we can do with trigonometric substitutions. I think the key of using trigonometric substitution or when to use it rather, is to identify situations where you have square roots of quadratic expressions. So, for such a situation, the idea is to use trig identities. Get rid of square roots. In the form number one form is 1 minus x squared. Number two form is 1 plus x squared. And number three form is going to be x squared minus 1. Because no one likes to see square roots. So how do we get rid of them? For this quadratic expression right here, notice that if we substitute x equals to sine theta or cos theta, we can use one of those identities over there to transform this into a cos squared or a sine squared, which cancels out with a square root, and you're left with a single sine or a cos. So let's just say we use a substitution x equals to sine theta. Then we can get the result. This is going to be square root of cos squared theta, which is going to be cos theta. Now, one thing to note is that I think you'll have to specify on your exam what range of theta does this work. Because otherwise, this should be having an absolute value sign over it, and integrating an absolute value sign is not a pleasant thing to do. So we're going to specify right here the range for which cos is going to be positive, which is pi over 2, small n over theta, small n over pi over 2. And then in this case, again, applying the same methodology, we want to use a trigonometric substitution to make this expression into a square, which cancels out with square root. So which one should we use? Notice that I think the third one I wrote down is secant squared equals to 1 plus tangent squared. So 1 plus tangent squared right here is what we want to use. And that's going to give us square root of secant squared theta, which is going to be equal to secant theta. And I think this will work for, again, that. And if you're not sure about the range of these things, just draw a sine curve or cosine curve on the exam, and I'm sure you can figure it out. And the third case right here is x squared minus 1, and notice that if we're substituting x equals to secant, now we're going to get square root of tangent squared, which is equivalent to 10. And this is going to be 4. 0 smaller than equal to theta, smaller than pi over 2. So I think this is probably the hardest part of using substitution. Let's use an example. A very simple one. Integral of 1 over square root of 4 minus x squared. This is going to be equivalent to, if we recognize the form square root of 1 minus x squared here, and use the substitution. Let's just say that x equals to sine of theta, then dx is equivalent to cos theta d theta. Now notice there's something different from traditional substitution in this expression right here. usually what we do is we recognize a block of expression in the integrand, and then we say that expression is u. And then we derive it, and then we put pieces together to integrate. But in this case, we're letting x itself be an expression. So I guess trigonometric substitution is different from traditional substitution in this sense. So this will become integral of 1 over square root of 1 minus, we let x equal sine here, so it's going to be 1 minus sine squared theta. And then dx, my bad, didn't write dx right here, equals to cos theta d theta. And using the trigonometric identity, we're going to get this is equivalent to cos theta over cos theta d theta. So all of a sudden this hugely complex, maybe not hugely complex, fairly complex expression turned into integral of d theta, which is just theta. Right, so here comes the last part of our integration by substitution using trigonometric identities, which is that we have this expression which is the final result of our integral, which is theta. But how do we convert theta into an expression back with x? Well, we use the expression right here. X equals to sine theta, so that implies that theta is equivalent to arc sine of x. And this is the format that I use for all of my integrations right here, where I'm going to write let u equals this, du is going to be equivalent to that, and in terms of trigonometric substitutions, I'm going to both express x as something of theta and theta as something of x. So that, I think that really helps clarifying the relationships between different substitutions, especially when you have more than one substitution sometimes going on. And going back to the example, we have theta as our final expression. Theta is equal to arc sine of x. So this is arc sine of x plus a constant. So I think that was relatively simple. All right, so I'm going to give you an example from the winter 2010 midterm now. So this is the winter 2010 midterm, question 1c. Integral of 1 over 1 minus x squared to the power of 3 over 2 dx. Maybe immediately this doesn't look like a quadratic form inside of a square root, but if we realize that the power of 1/2 is just square root, then this expression will become square root of 1 minus x squared cubed dx. Again, we use the same substitution as in the last example. Let x be equivalent to sine theta. Then dx is cos theta d theta. And then I'm also going to write here that theta is equivalent to arc sine of x for the last step. So then this expression right here is going to become 1 over, I'm going to skip one step right here, which is that 1 minus sine squared is cos squared. And then square root of cos squared is just cos, so that's going to be cos cubed of theta. And then substituting dx right here, I get cos of theta, d theta. Right? So that the cos theta and the cos cubed theta cancels out, which gives me the integral of 1 over cos squared, which is equivalent to the integral of secant squared theta. Now the integral of secant squared theta, this is the part where you need to recognize that the derivative of tangent is secant squared. So this right here is exactly tangent theta plus c. And I'm going to give you a list of common trig integrals right after this example, which has one last step to complete. How do we convert tangent theta plus c? C is constant. How do we convert tangent theta into an expression with x? I'm going to write it right here. And this is where we use the right angle triangle. Theta is an angle, as we all know, if you plug in, the input to a trigonometric function has to be an angle. So let theta be this angle of a right angle triangle. What do we know? We know that x is equivalent to sine of theta. And sine of theta is this side over this side right here. So if we let x be this side and 1 be length this side, then we have satisfied the condition that sine theta is equivalent to x over 1, which is equal to x. And from that, we can figure out what tangent theta is. Tangent theta is just this side over this side, rise over right. And this side right here, by Pythagorean theorem, is 1 minus x squared. Right, so in this case, we can write tangent theta is equivalent to x over square root of 1 minus x squared. And so this expression eventually turns into x over square root of 1 minus x squared plus c. And the general flow of trigonometric substitutions, unless you have a very simple one like that where you end up with just theta, is going to be you substituted x with some trig of theta, and then at the end you end up with a different trig, which is tangent or secant or whatever. And eventually you're going to have to draw your right angle triangle and figure out which sides you want to use for the final reverse substitution of theta back into x. Does everybody have this table right here? Can I erase it now? Yeah. And does anybody have any questions so far? Okay, so that wasn't very difficult, was it? That was the midterm. So in terms of the midterm, I expect your midterm to have, I think half of it will probably be integral and different kinds of integrals. Substitution, trigonometric substitution by parts, partial decomposition, and things like that. So I'm going to spend a lot of time doing examples on these. All right. Right, I said I was going to give you a list of common trig integrals. I'm sure you've seen some of these before. Let's just start with the easiest one. Integral of sine x dx is negative cos x plus c. And integral of cos x dx is equal to sine x plus c. For some of the more difficult ones, we're going to have integral of tangent x dx is equal to ln of secant x. And that, I'm actually going to illustrate right now. This is going to be equivalent to integral of sine x over cos x. And excellent opportunity to illustrate the integration by substitution, where we let u equals to cos x, and du is going to be equivalent to negative sine x. Notice one thing is that even though we can let u be sine x and du will automatically be cos x, we cannot have a situation where du is on the denominator of a fraction, because that would result in something like this one, which you can't integrate. Du has to be, a standalone term that's on the numerator. So in this case, we have to let u be equivalent to cos of x, and that way the sine x dx will turn into negative du, which is on top. And allows us to integrate. So I'm going to write that down. Equals the integral of negative du over u, which is negative ln u plus c, which is negative ln secant of x plus c, which is a little strange to me because I didn't expect this negative return. x cos x. Can you guys spot an error in this integration right here? B equals cos x and du is equal to negative sine x dx. It's fine, and right here negative du over u, which is negative ln u plus. So I think I was missing a negative sign in the beginning. All right, so number 4, integral of secant x dx is equal to ln of sec x plus tan x plus c. And then number 5, integral of secant squared x dx is equal to tan x plus c. And the last one, integral of tan x sec x is equal to secant x plus c. All right, and this comes from the fact that the derivative of secant x is just tan x times secant x. So this might be useful when you're integrating something and it ends up being something of this form, and then obviously I think the most difficult one to remember is this one right here. And it's very difficult to do this integration if you don't know that that is the right answer. All right. So sometimes we don't exactly have the standard forms as indicated there. We don't have square root of 1 minus x squared. We might have square root of 4 minus x squared. And I'm going to illustrate with an example right here where we have square root of x squared plus 4 instead. So we can recognize the square root of x squared plus 1 form. And then what we're going to try to do is try to convert this into the standard form. Convert square root of x squared plus 4 into something x squared plus 1. And how do we do that? In this case, it's very easy because square root of x squared plus 4 is square root of 4 x squared over 4 plus 1 equal to 2 square root of x over 2 squared plus 1. And then what are we going to do? Once we have this standard form right here, we're going to let whatever this is be equivalent to the substitution we're going to make. So usually what happens is we have just x squared plus 1, and we let x in this be equivalent to tangent of theta. But in this case, we have x over 2 squared plus 1. So what we're going to do is we're going to let x over 2 be equivalent to tangent of theta instead. And the reason for that is that our trigonometric identity only works as 1 plus tangent squared. If we have 4 plus tangent squared, that's not going to give us the secant square that we want, and that's the substitution wouldn't work in that case. So I'm going to write down a few more lines of details that implies that x equals to 2 tangent theta, and that dx is equivalent to 2 secant squared theta d theta. And theta is also equivalent to arctangent of x over 2. And I believe all of these lines of information will be used later on in the integration step. So now that we have converted into the standard form, we're going to write the integral again as x squared times 2 times the square root of brackets x over 2 squared plus 1, which is going to translate to, using the substitution x equal to 2 tangent theta, it's going to be 1/2 integral of 1 over a very long expression, 4 tangent squared theta times square root of x over 2 is just tangent theta, so that's tangent theta squared plus 1. Using the third identity over there, that gives me secant squared, which is square rooted into secant theta, and on top, dx will turn into secant squared theta d theta. I believe that's correct so far. That's going to give me, right, this is actually going to be 2 secant squared theta. Yeah, right. And then the 2 and the 4 cancels out of it, and then take it out, you get 1 over 4 again. And we have sec theta over tan squared theta d theta. When you see an expression with secant and tangent that you cannot integrate directly, or if it's difficult to integrate directly, try converting these into their sine and cosine form. So I'm going to go right over here and convert them. 1 over 4. 1 over cosine theta, because secant is 1 over cosine, and tangent is sine over cosine. So we can cancel the cosine out. Oh, actually, can we? Nope. I was missing the square. Because it's tangent squared over here, gives me sine squared over cos squared. And that will give me 1/4 cos squared, cos theta over sine squared theta d. You can probably see from this step now that we can apply our regular substitution again, where u is equivalent to sine theta and du is equivalent to cos theta d theta. And this integral will translate to integral of 1/4 du over u squared, which is going to be, I'm just running out of space here, 1 over 4 negative 1 over u. Because negative 1 over u is negative u power of negative 1. Drop down the coefficient at the power and then subtract 1, you will get u negative 2, which is 1 over u squared. And that will be the final result, but we have to reverse the substitution back twice. So we first reverse u to theta, and then we have to use this theta right here and convert it back to x. And later on you'll see an example where I'll have to do 3 substitutions, and you have to reverse it one by one. Okay, so I probably should erase the rest. I wish these blackboards have an automatic eraser. Then I don't have to do this all the time. Right. Negative 1/4 u plus c is equivalent to u is sine theta, so that gives me 1 over sine theta plus c. Right, and then now we're going to have to use our right angle triangle again, as I told you that when we're reversing the substitution between x and theta, we're going to have to use the right angle triangle, and to begin with, we see that x over 2 is tan theta. I'm going to write it down here. Tangent theta is x over 2. Right, so let theta be any angle, it doesn't matter. Tangent is this side over this side. So we let this side be x and this side be 2, and we have satisfied the condition tangent theta equals to x over 2. Now what is sine theta going to be? By Pythagorean theorem, we're going to see this side is 4 plus x squared. And this should ring a bell because we started with x squared plus 4, square rooted. And again, using the definition of sine, we're going to see that this is equivalent to x over square root of 4 plus x squared. And hence, making the substitution, negative 1 over 4 square root of 4 plus x squared over x plus c. That was a fairly long example. All right, the key takeaway for this example right here is to recognize that if we have the form ax squared plus b, or ax squared minus b, or b minus ax squared, then what we got to do is we got to take out the b to scale this term down to 1. This will allow us to use the trigonometric identities that I've included in there and make the trigonometric substitution. So, for example, I'm using this one right here. The first step is to scale the b down to 1, and we do so by factoring out b. Right, so square root of b over b x squared plus 1. And then we can take out the square root of b and express what's inside as square root of a over b x bracket squared plus 1. All right, I know this is kind of abstract, but I hope I've illustrated the example over here, which is easy because a is 1 and b is 4 squared in this case. So these 1 and 4 are both squares, so this expression right here is going to be an integer. And after you see that, as I said over here, I'm going to let whatever is inside of the bracket be equivalent to the trigonometric function. In this case, we have the form x squared plus 1, so we use substitution tangent squared, and that will give us let square root of a over bx be equivalent to tangent theta. And so whatever is inside the bracket will turn into tangents, say theta, and this entire expression will become secant squared, which is just secant in the end. So that's kind of the general approach to do this kind of problems. Now we're going to move to even more complicated cases. What happens if we don't have that nice expression over there? What happens if we have a quadratic with a linear term in the middle? Alright, so let's say we have the form square root of ax squared plus bx plus c. This isn't as nice. We can't scale everything down and just get rid of the linear term. That prevents us from using the trigonometric substitution directly. So what we have to do is complete the square. Let's ignore the square root for a second. I'm not sure if you learned completing the square in high school. Probably would have during the solving the quadratic functions part. But just in case you forgot about that, let's revisit it again. So ax squared plus bx plus c is equivalent to ax squared plus bx, ax squared plus b over ax plus c. All I'm doing is I'm just factoring the a out of the first two terms. Now comes the completing the squared part. X squared plus b over ax plus b squared over 4a squared. Let me express that more nicely. So it's b over 2a squared. So why am I doing this? Why am I adding a term at the very end? I'm trying to complete the square, so as you know that x plus, let's say, some kind of constant k squared is going to be equivalent to x squared plus 2k plus k squared. So in order to make this into a square, having the first two terms, I'm going to match these two terms. X squared is already matched. The coefficient, sorry, 2kx, is 2k over here and b over a over here. So if I just let k equals to b over a over 2, which is b over 2a, I'm going to know that the final term of this squared expression, quadratic expression,